Well, one of my students asked me for help with this problem, and I thought it was a pretty good problem, so I thought I would make a video and then we could all learn from it. So here's the situation. We have a large mass that I'm labeling with a big M, and a small mass that I'm labeling with a little m. And then there's a force acting just on the small mass at the top. And there's also two forces of friction at play that we have to take into account. So first of all, there is a coefficient of static friction that characterizes the interaction between the small mass and the large mass. And then there's also a coefficient of kinetic friction that characterizes the interaction between the larger mass and the ground. And the question wants us to determine what F is here, what this force is, in fact, what the maximum value of this force is, such that there is no relative motion between the little mass and the bigger mass. So what is the maximum force that we can apply to this upper mass such that there is no slipping of the little mass on top of the larger mass? Okay, so the parameters are given as the little mass is 2 kilograms, the larger mass is 3 kilograms, the coefficient of static friction is 0.8, and the coefficient of kinetic friction is 0.2. And these are unitless. One way we can remember that, or to see that, is to remember that the frictional force, FF, let's say, is equal to the coefficient of, let's say, static friction times the normal force, right, at that interface. And if FF, which is a force of friction, if that's a force, it has the units of newtons. And N is a force, it's a normal force, it also has units of newtons. So in order for this equation to make any sense, mu s better be unitless. Otherwise it doesn't make sense. That's a little tangent. Okay, so let's start by drawing some free body diagrams. It's always a good place to start in these problems. So let's begin with the little mass, m. And I'll do it over here. So I'll put the little mass, m, right here. So what do we have going on? Well, first of all, there is a normal force acting upwards from the larger mass pushing up on the little mass. There is a gravitational force because this thing has mass, so its weight is pulling it downwards. I'm just going to write it as mg because we can all skip that step. Now, what else is going on? Well, obviously this force F is pushing the little mass in that direction. And then, because there's friction, the larger mass is going to resist the motion of this upper mass. So we'll have a force of friction in the opposite direction to the motion. Okay? So let's choose a coordinate system. Pretty obvious what to do here. We choose x and y just because everything is in that plane and along the x or y axes. And let's sum forces about, let's begin with the y direction. So here we have n minus mg equals what? Equals the mass times the acceleration in the y direction. Well, it's just resting there in the y direction anyways, so this is going to be 0. There's no acceleration vertically. And from that we can say right away that n is equal to mg. Actually, a lot of my students will often jump right away. If ever there is a normal force involved, just go right to saying that n equals mg. And it's true in this case, but as we'll see with the larger mass, you can't just jump right ahead and say n equals mg. You have to, write out your sum of the forces and set it equal to the mass times the acceleration, and then you'll be able to relate the normal force to the force of gravity. So here it works fine, but this is not true in general when there's more complicated dynamics going on. Anyway, that's a bit of an aside also. So let's sum the forces in the x direction. Well, we have a applied force, F, and then we have a frictional force, FF. And, well, since FF is equal to mu Sn, okay, we can just say that this is going to be F minus mu Sn. And what is this equal to? Well, it's going to be equal to the mass of this guy times whatever acceleration it's experiencing in the x direction. But the question is asking us to find this force when the relative acceleration between these two bodies is 0. That is, m is not slipping, m is not accelerating faster than, little m is not accelerating faster than large m. So even though there is no relative acceleration between these two bodies, there may still be an overall acceleration, right? So let's imagine that m is moving at some constant acceleration. It can still be the case that there is no relative acceleration between the two bodies if the upper m is also accelerating at that exact same acceleration. So at this point, we can't say that a equals 0 because we don't know if a equals 0. And in fact, there's a bit of a hint in the question because we're given a mu k, and that implies that there's some motion, right? So for now, let's just write this as ma. We don't know what a is just yet, but we're going to keep in mind that whatever this a is, when we get to the free body diagram for m, these a's better be the same, okay? So, can we do anything else with these equations? Well, we also know that n equals mg, so we might as well just put that in if I just write out one more line. And just to make it super fancy, where all I've done is a little bit of algebra here to isolate for f, because that's what we're going to be wanting to solve for later. Okay, so we're done with this m. We're done with this m. This is confusing. It's hard to be precise about what I mean when I say m and m. But hopefully it's clear from the context. Okay, so on to the free body diagram for the larger mass. Big M, capital M. So let's put it here. And okay, so what's going on? What's at play? Well, first of all, it has a mass, so it's going to be some gravitational force, mg, big mg pointing downwards. Now, remember that if we have a normal force on the little mass from the larger mass pointing upwards, since there's no relative motion between these two bodies, the little mass is going to act back on the larger mass with an equal and opposite normal force. So there's going to be actually another n pointing downwards here. Oops. And that is coming from the little mass sitting on top of the large mass, right? But actually, that's not the only normal force at play, right? Because we have another normal force from the ground pushing up on the larger mass m. So we're going to have another n acting upwards. However, this is not necessarily, in fact, in general, it's not the same n as the initial one here. In fact, it won't be, I said, in general it won't be. It won't be, because this normal force has to overcome both of these masses. So, not to confuse anyone, let's relabel one of these. So this was the one from our original diagram, N1. So I'll just write it as N1 everywhere to make sure we're not confusing ourselves. N1. Okay, and then I'll call this one, let's say N2, because I'm feeling creative today. Okay, so just to reiterate, we had the gravitational force from this large mass pointing downwards. We had this N1, which was coming from the little mass sitting on top of the large mass. Remember, this was the free body diagram for the larger m. And then we have this other normal force, which comes from the fact that the larger mass is sitting on the ground and not falling through it. So clearly the ground is acting upwards on that one, on the larger mass. So we have an N2. Now, we also have a frictional force here, which is acting at this interface between the larger mass and the ground, and that's going to resist the motion of M. So presumably if there's a force being applied here, this whole system may be moving to the right. So let's put that frictional force in the opposite direction to the motion. So we're going to have an FF here. And now, again, we have to be careful with our notation because this FF is different than that FF, right? That FF came from the interaction at this interface. This FF is coming from the interaction at this interface. So let's call that FF2, okay? And we know that that's actually going to be equal to mu k times n2 now, because the normal force that is coming from this interface goes into the formula for the friction at this interface. And let's call that first one, I'm just going to go back and relabel it FF1 everywhere that it shows up, just to be crystal clear. I think that's everywhere, okay. So we have this FF2, and we're not quite done, because actually, we have another frictional force to worry about. So this FF1 actually appears in our diagram. And if you think for a second, so this is another tricky part of this problem, and one of the reasons that I decided to make a video about it is because we actually have the frictional force so let me be crystal clear. The frictional force that the large mass experiences at the interface between the two masses is actually pointing in this direction, okay? And why is that? Well, if we go back to our free body diagram for the little mass, here, the little mass is trying to move to the right, and the larger mass is resisting that motion, so it's causing a force backwards. But if you think about it from the point of view of the larger mass, right, there's this little mass dragging it. There's this little mass moving to the right on top of the large mass, or trying to move to the right. And so in fact what's happening is this little mass is dragging the larger mass with it. So we have that same frictional force acting in the opposite direction as it was in the first case, because now the little mass is dragging the upper mass. So we have an FF1 here. And we remember that this is going to be mu s n1. n1 because it's the normal force at this interface where this frictional force is coming from. Okay? So that's the tricky part to this problem. Once you have that, it basically just comes down to writing out Newton's laws. We already did that for the first one, so let's do it for this guy. So if we sum the forces in the y direction here, and I'm going to use the same coordinate system as before, y vertically and x horizontally, we have, n2 minus n1 minus mg, mg equals 0. Why does it equal 0? Well, large M is not moving in the vertical plane, so there's no acceleration there. Okay, let's rewrite this. It's a little foreshadowing here, but why am I choosing to write it like this? Well, presumably we're going to want, when we sum the forces in x, one of these normal forces in terms of the other one. So I'm going to choose to write n2 in terms of n1, but you'll see why that happens in a second. Okay, so here we have two forces. We have the frictional force to the right, so that's a mu s. Well, yeah, I'll just write it out. Mu s n1, and then we have this force resisting that, so it's minus mu k n2. And that is not equal to 0, but in fact it's equal to, well, mass times acceleration, right? So we have the larger mass. Why the larger mass? Because this is a free body diagram. of the larger mass. So we use its mass in our equations of motion. Excuse me. And the acceleration is a. It's the same acceleration as we have from the little mass. So, just to repeat it now that we can see the whole picture, even though the little mass is not supposed to slip from on top of the larger mass, the whole system is still allowed to be accelerated to the right, for example. And that's the direction it would accelerate, because that's the only force at action. Excuse me, let me take some water. Okay, and so even if these two masses are accelerating to the right, as long as those accelerations are equal, as long as the acceleration of the upper mass always matches the acceleration of the lower mass, well, the little mass is not slipping, okay? So what do we do from here? It's really a simple matter to just sub in, well, let's sub in what we had for N2 here. So mu s N1 minus mu k, just gonna sub this in. Right? And in fact, we know that N1 is just mg, right? So we have mu s mg, and we know that from this equation right here. Mu s mg minus mu k mg plus m, big mg, equals big M times A. Okay? And we know everything in this equation, so we can just solve for what A is, right? And if we do that, you'll find, I'm not sure if I'm going to run out of room, so I'll just write the answer over here. If we solve that equation, we solve this equation down here, we'll find that A equals 1.962 meters per second squared. And that comes from solving this equation. Just plugging in what we, just plugging in all the variables, okay? And then finally, all we have to do is go back to our equation over here. Our F equal to m times this thing. And now that we know the acceleration, we just plug that in. And if you solve for F, you'll find that, oops, F equals 19.62 newtons. And yeah, that's the way to solve this problem. Okay, kind of a fun one because of this little trick with the relative accelerations. But now that we've thought about it, it's really not that hard.